Okay, in this presentation we are going to look at De Morgan's laws, this time in the context of probability. Now you probably have seen them before in set theory and in logic, but here we will apply them in the context of probability. De Morgan's laws are fundamental in set theory and have important implications in probability theory. They provide a way to express the complement of the union or intersection of two events. Okay, for an undergraduate discrete maths course, that's probably as far as we will be going, union or intersection of two events. But you could sort of expand it out a little bit more. It's complicated, but it's not impossible. Anyway, so we have two laws. There's the complement of the union and the complement of the intersection. Okay, so first off, let's look at the complement of the union. And to start off, we have the complement of the union. So the union is A union B. The complement of that is complement of A union B. Okay, and we're interested in the probability of that. But how we might re-express that is as follows: the probability of the complement of A intersected with the complement of B. Okay, so essentially just notice that we have the union symbol on the left-hand side of the equation, but the intersection symbol on the right-hand side of the equation. Okay? Interpretation: the probability that neither event A nor event B occurs is equal to the probability that both event A does not occur and event B does not occur. Okay, so complement of the intersection. Okay, very similar. It's actually almost like a mirror image, but let's read it out. So we have the intersection of A and B, and we're interested in the complement of that. So we have the complement of the intersection of A and B, and we're interested in the probability of that. Okay, so that's the left-hand side of that equation there. And that is equal to the probability of the complement of A union the complement of B. Okay, interpretation: the probability that not both A and B occurring is equal to the probability that either A does not occur or B does not occur, or neither occurs. Okay, a little bit clunky actually to verbalize it, but I think a better way is actually to try and visualize it. I think this actually really helps us get a proper intuition for De Morgan's laws, and I have something similar to this in the context of set theory and logic. Okay, so we have a universal space here, which is pretty so essentially we have a rectangle here which represents the possibility of all possible outcomes with regards to A and B. Okay, so and it's broken up into four regions: 1, 2, 3, and 4. 4 being the region outside A and B. Okay, so we have an event A, which is the regions 1 and 3. Okay, 3 being the intersection of A and B, but it's part of A, and the complement of that is 2 and 4. Okay, so B, that's not the part of B that's not part of A is region 2. And the region that's outside both A and B is region 4. Likewise, we have event B, the regions 2 and 3, and the complement of that is regions 1 and 4. Okay, so let's look at this a bit closer. So we have the union of the intersection, the union of the complement of A and the complement of B. So the complement of A is 2 and 4, regions 2 and 4, and the complement of B is regions 1 and 4. So the union of those two events is regions 1, 2, and 4. Okay? Now, the intersection of the complement of A and the complement of B is which regions occur in both A, complement of A, and complement of B, region 4. Okay, so that's enough to get going with so far. So law 1, which is the complement of the union. Okay, so recall that the union of A and B is regions 1, 2, and 3, and the complement of that is region 4. Okay, actually, sorry, this is the first time we introduced the A union B. So that is 1, 2, and 3. Okay, the complement of that is region 4. Recall that the complement of A intersected with the complement of B is also region 4. So essentially, that just sort of proves the point there. And that just sort of substantiates the relationship there between the complement of the union and the intersection of the two complements. Okay? And law 2 is very similar. So we have A intersection B, which is region 3. The complement of that is regions 1, 2, and 4. And recall that the union of the complement of A and the complement of B is 1, 2, and 4. So therefore, we could say that the complement of the intersection of A and B is equal to the union of the complements, complement of A and complement of B. Okay. So I think that really emphasizes the point and gets across nicely, this visual setup using these diagrams. Okay, so quick example and we'll finish it up. So imagine you are flipping a coin twice. Event A, getting heads on the first flip. Event B, getting heads on the second flip. A union B, the event that you get heads on at least one of the flips. And the complement of that is that you get tails on both flips. Okay, so the complement of A, the event that you get tails on the first flip. The complement of B, the event that you get tails on the second flip. And that is the A intersection B. A complement of A intersected with the complement of B is that you get tails on both flips. So essentially it just sort of demonstrates it as well, just to sort of think of a work example like that if the visual approach does not help you. Okay. So the key takeaways: De Morgan's laws provides valuable tools for manipulating and simplifying probability expressions. They help express complex events in terms of simpler ones. And these laws have applications in various areas of probability and statistics, as well as set theory, logic, and circuit design. Okay, they can be extended to more than two events, and they are closely related to the laws of Boolean algebra. In fact, you will probably see them directly in Boolean algebra. Okay. Right, we'll leave it there. I think that's everything. Yeah, that's everything. We'll leave it there.